Welcome to Anna ARM YouTube channel, your trusted hub for training in solar photovoltaic system installation and maintenance. Today's topic is energy bans in solids. This topic is quite unique because it connects both chemistry and physics. Now, clear, just to be clear, you are not we are not promoting any specific textbook. But if you would like to explore this topic further, here are some helpful cross references. Chapter 13, New School Physics for Senior Secondary Schools, 2016 edition. Chapter 4, New Chemistry for Senior Secondary Schools, 2016 edition. Our learning objectives for this topic are as follows. 1. Explain the terms valence band and conduction band. 2. Discuss how the band gaps affects electrical conductivity in solids. 3. Give reasons why metals conduct electricity better than insulators. 4. Describe what happens to electrons in a semiconductor when it is exposed to sunlight. 5. Why is silicon preferred for photovoltaic cells compared with metals or insulators? Before we dive in, let's quickly revisit some foundational topics that will help you better understand this concept. What are these topics? 1. Introduction to solar. 2. Components of solar radiation. 3. History of photovoltaics. 4. Importance of solar energy. 5. Applications of solar energy. And 6. Basic internal structure of photovoltaic cells. If you haven't watched those lessons yet, I highly recommend you do. They will give you the strong foundation needed to fully grasp today's discussion. Let's get started with energy bands in solids, a fundamental concept that explains how electrons behave inside materials and why some materials conduct electricity while others do not. Every material, whether a metal wire, a sheet of glass, or a silicon wafer, contains billions of atoms arranged in a regular pattern. Each atom has electrons that occupy specific energy levels. When atoms come together to form a solid, these discrete levels interact and spread into bands of energy. The most important of these are the valence band and the conduction band. Now, valence band and conduction band. For the valence band, it is the band that contains the outermost electrons responsible for bonding between atoms. These electrons are usually bound tightly to their atoms and cannot move freely. Conduction band. The band where electrons are free to move throughout the solid, carrying electric current when a potential difference is applied. Then the band gap. The energy difference between the valence band and the conduction band is the band gap or energy gap. The size of this gap determines whether a material conducts electricity easily, hardly at all, or under certain conditions. Let's take a look at the diagram. Here is the diagram representing the energy band. This is the conduction band and this is the valence band. The gap between them is what we call the band gap. So we are coming to that later. Classifications of solids by energy bands. We have conductors. In conductors, e.g., copper, aluminium, silver, the valence band overlaps with the conduction band, or the conduction band is partly filled with electrons. Because of this overlap, electrons move freely even with a small applied voltage, resulting in very high electrical conductivity. Metals are excellent conductors and are used for solar wiring, connectors, and bus bars in photovoltaic systems. Insulators. In insulators, e.g., glass, rubber, plastic, the band gap is large, typically greater than 5 electron volts. This is what we mean from this diagram. This is insulator. So you notice that the gap between the two bands is very large. Electrons in the valence band need an enormous amount of energy to jump into the conduction band from the valence band. So almost no current flows. Insulating materials are used in PV systems for cables, junction boxes, and protective casings to prevent short circuits and electrical shock. Now, semiconductors. In semiconductors, e.g., silicon, germanium, gallium arsenide, The band gap is moderate, about 1 electronvolt. Let me take you back to the diagram. This is what they are referring to. This is semiconductor. You notice that the band gap is narrow. At low temperatures, few electrons occupy the conduction band, so the material behaves like an insulator. But as temperature increases or when light strikes the surface, electrons gain enough energy to cross the gap, leaving behind holes in the valence band. These free electrons and holes act as charge carriers, con- making the material conductive under suitable conditions. This property makes semiconductors ideal for solar cells because sunlight can provide the energy needed to promote electrons from the valence to the conduction band. Now, band structure and the light interaction in solar cells. When sunlight, otherwise called photons, hits a semiconductor such as silicon, the photon's energy can excite an electron across the band gap from the valence band to the conduction band. This is what they are referring to. From these valence bands, electron can be excited from this region to the conduction band in a semiconductor. This process creates an electron hole pair. The p-n junction inside the solar cell then separates these charges, allowing electrons to flow through an external circuit and generate electric power. Fourth, understanding energy band theory explains why a solar cell can convert light into electricity, a concept elaborated in the next section on the basic working principle of photovoltaic cells, which we shall discuss in the next video. In summary, energy bands arise from the interaction of atomic energy levels in solids. The band gap determines whether a material is a semiconductor, insulator, or a conductor. Conductors have overlapping bands, which are called free electrons. Insulators have large gaps, no conduction. Then semiconductors have small gaps. Conduction increases with either temperature or light. The behavior of semiconductors under light is the foundation of photovoltaic technology. I repeat, the foundation of semiconductors under light is the foundation of photovoltaic technology. That brings us to the end of today's presentation on energy bands in solids. I hope this lesson has helped you understand this concept more clearly and that you now feel more confident discussing how energy bands affect electrical conductivity in materials used for solar photovoltaic systems. As a recap, We believe you can answer the following questions. 1. Why is silicon preferred for photovoltaic cells compared with metals or insulators? 2. Describe what happens to electrons in a semiconductor when it is exposed to sunlight. 3. Give reasons why metals conduct electricity better than insulators. 4. Discuss how the band gap affects electrical conductivity in solids. And 5. Finally, explain the terms valence band and conduction band. If you found this video helpful, don't forget to like, subscribe, and turn on the notification bell so you never miss another lesson. You can also share this video with your classmates, colleagues, or anyone interested in renewable energy and solar PV systems. And remember, your feedback matters. Drop your questions or comments below. I will be happy to respond. Thank you so much for watching Anna ARM. Until next time, keep learning, keep growing, and keep building a sustainable future.